Hello, everyone, and welcome to another day together. Our focus today is on dilutions. This is day 3 of Unit 10. As it mentions, if you have not already watched the Zoom meeting from today, would you please go back and watch that? Not only does it do some review from the previous day, it also gives a little bit of context about what you're going to be learning today. So assuming you've done that, let's get started. Your objective today is to focus on how to dilute a solution and then to calculate the new molarity. So qualitative and quantitative, and also kind of thinking about lab procedure. Go ahead and set up your EQ, which will give you a guide for what you should know by the time you're done with the lecture today. It also helps you write your summary. Let's get into it. All right, so dilutions is our focus. So a couple terms just related to this that I want you to be in agreement on is a dilute solution is generally something that has a smaller amount of solute. Now, it has to be compared to something else. So dilute would generally mean smaller depending on what you're comparing it to, but generally there's a smaller amount of solute. A concentrated solution has a larger amount of solute. So if you look at this visual here, so in this case, between the two particle levels, you can see that the blue particles are the solute, giving it that blue color. And when there's a lot of those particles, that would be more concentrated. There's more solute in the amount of solvent that's given, so it gives it a darker color. There's more solute in the area, so then that's concentrated. A dilute solution, as you can see here, it has less particles of the solute per the amount of solvent, so then that ends up being more dilute. So that's just kind of the general. Here's a visual, kind of help you. Here's a particle level, kind of help you think of it too. Generally, if you have a solution that is too concentrated, if you want to dilute it, generally, if you look at the difference between this and this, what you do is you add more solvent. So the reason that's super useful is because you haven't changed anything about the solute itself. You changed the solvent because it's pretty hard to remove solute. Like, so in terms of making something diluted, if you wanted to get a smaller amount of solute, it's pretty hard to remove that. But you can easily add more solvent. So the reason that's useful is because that means you haven't done anything to the moles, which is good because that's harder to measure. But you have changed, especially like in this example, you have changed the liters of solution. So the liters after is higher than the liters before. So even though these two beakers have the same moles in them, the molarity or the concentration changes because you have increased, in this case, you increased your liters. So then if you think about our molarity equation, which is moles per liter, if the moles stays the same, but the liters gets bigger, you're dividing by a bigger denominator, so your molarity will get lower. Well, that also makes sense because if something is dilute, it has less stuff per amount of solution, so then that has a smaller concentration. All right, so that's kind of the idea behind dilutions. Here is what we do with it. So here's the useful trick. We know that this is what molarity is, moles of solute divided by liters of solution. But if we rearrange it to focus on the molarity and the liters, because that's what's changing, little algebra, we get this. Moles of solute equals liters of solution times molarity. Okay, so that's true. But remember what we just said on the previous one. The moles of solute is not the thing changing. So the moles of solute before is equal to the moles of solute after. All right, so then that means that we could do a substitution. And if we plug this information for before and this information for after, we end up something that looks like this. The molarity before and the liters of solution before would equal the molarity after and the liters of solution after, because this equals this, this equals this. It's that lovely transitive property from math, right? If these two things are equal to each other, then this is equal to this, and so is this, and then they're equal to each other, right? That's the transitive property. So then the equation that we build from this, because this is just a unit, right? It's not a measurement. So molarity is a measurement. So we want to turn these both into measurements. So M1 V1, so that's liters V1 equals M2 V2. This is known as the dilution equation, and it's a nice little algebra problem. So like if you know your starting molarity and how much you measured, and you add a bunch more water to dilute it, you'll know your new volume. you can solve for your new molarity. And it turns out that this is probably the number one equation I use when I'm preparing lab solutions for us in class. The molarity that we buy from like our suppliers is really, really high because then we can use it for a long time. So I measure out like the really high, some amount of the really high concentration. I add a bunch of water to get to whatever I need for the lab. And then that will give me the molarity that we're looking for. And I can figure out, and I could do it the other way. If I need to have a certain molarity for a lab, and I need to have a certain amount of that, maybe for all the different classes, then I can figure out how much volume do I need to measure out of the really strong stuff, and then I can do it that way too. So dilution equation works both ways, and it's a super useful trick in the chemistry world. All right, here's an example. Imagine that I had 25 milliliters of a 1.0 molarity copper sulfate solution. I dilute it to 750 milliliters. What would be the new concentration? So here's you can see on the graduated cylinder, here's my 25 milliliters of a 1.0 molarity copper 2 sulfate solution. I know it's copper 2 because sulfate is a -2, so the copper has to be 2 to balance it. So this is what I measured out. It says that I'm diluting it, so just to review, generally what do we do when we dilute something? You're right. I'm going to add more solvent. And in this case, this is an aqueous solution, so I'm going to add some water. So if I measure this out, my 25 milliliters, and I add a bunch of water, I want it to be specifically to 750 milliliters. Maybe that's how much I need for a lab we're going to be doing. And so then I need to figure out what the new concentration is, because if I don't know that concentration, then I can't do calculations with it. Okay, so here's my 25 milliliters. I'm going to put that in my beaker, and then I'm going to add a bunch more water until I get to 750 milliliters. Visually, we can already see that this is a lower concentration, but we want to figure out exactly how much lower. We're going to use the dilution equation. We're going to plug in what we know from the givens in the problem and solve for what's missing. So I've got a volume here. So my initial volume was 25 milliliters. My initial molarity was 1.0 molarity. That was given. I added a bunch of water until my new volume was 750. So then really what I'm solving for is M2. So I plug in what I know, right? 1 molarity, 25 milliliters was my initial, my before. My after, my V2 is 750. I'm solving for M2. So I just did the algebra like this. You wouldn't have to write this step out. You could just do this on your calculator kind of in your head. Showing your work for just this part is enough. So then I can see that milliliters is going to cancel. I'm going to be left with molarity, which is what I want. And I end up with 0.033 with 2 sig figs, right? Because this has 2, this has 2, this has 2. So on your calculator, you'll chop it off with 2 sig figs, 0.033. So again, I knew it was going to be lower because I added a whole bunch of water and left my moles the same. So moles divided by a whole bunch more milliliters is going to be a lower concentration, but now I know the exact concentration. So again, this is a super useful equation for not just doing a qualitative dilution, like, I added more water and now it's a lower molarity, but to actually calculate. Or again, you could go the opposite way. If I know the molarity I want and I know the volume that I need of that, and I know what my starting, like we call it the stock solution, I buy from a company. I know that molarity. I can figure out how much of the really strong stuff do I measure out. And then I add water until I get to the volume I want, and then it will be the molarity that I want it to be. So that's a super useful lab equation. Again, a quantitative dilution problem, not just that it's a lower concentration. And that's it for today. So here's what I'd like you to do. I didn't have you do any COSTA questions yet because it was so short. So please go back and do the COSTA questions for these notes and do your summary from the day 3 notes that we just did. Remember that the solutions practice from day 1 and 2 of this unit should be done. It's due today, so please submit that. Of course, if you have questions, let me know. And then what I'd like you to do for the rest of our time together today is I'd like you to open the concentration PhET lab activity from Schoology, put it in Notability, and then there's a link to a website for the concentration PhET lab. So this is a cool lab because it feels like you're actually doing something instead of just watching. You can actually add water, remove water, add solute, different solutes, and then you're going to be sort of exploring concentrations and dilutions with that lab activity. Of course, I'm always going to make a plug for doing practice problems with this dilution stuff. It's nice to kind of just get a little bit more practice. And then we'll see you at our next Zoom meeting. Thanks so much for joining in. We'll see you next time.